those people who will be joining, some of them will be joining. We go share the screen. Pericyclic reaction 4. Oh, no, not this one. Microsoft PowerPoint. Yeah, I come here. You have the screen. Do you see the screen?
Yes, sir.
It is visible, right? Okay. So we start this topic of pericyclic reaction, sigmatropic rearrangement. So definition was already given to you. What is a sigmatropic rearrangement? We have to understand how it happens, what is the theory behind this. So this is what is there. It is the sigmatropic rearrangement. So it's a type of pericyclic reaction itself. Here, what happens here? A sigma bond is broken in the reactant, and a new sigma bond is formed. So we go to this pointer, and new sigma bond is formed in the product, and the pi bond rearranged. That means the number of pi bond remains same. The sigma bond that is broken, it can be in the middle, it can be in the end of the pi system. So the example, typical example that we have taken, it is the same example I am repeating. So here, what is there? This is a diene, but it is 1, 2, 3, 4, 5, 1, 5 diene system. And after this sigma bond is broken, and this new sigma bond is formed. But this sigmatropic shift is termed as 3-3 sigmatropic shift. Why this is 3-3, that also you have to understand. In this case, this hydrogen it is deuterium, which is here, migrates to this position. What it is? It is 1, 2, 3, 4, 5, 6. 6 atoms involving 6 different atoms, but it is this diene system. In the product, we have this 2 pi system, but new sigma bond, this bond is broken, and this bond is formed. This new bond is formed. So one thing that you see here, this is the 1-5 sigmatropic shift, and this is 3-3 sigmatropic shift. How do we give this name? This numbering, where from it comes? So let us understand this first before we go to the reaction. This is just next slide. Numbering in sigmatropic rearrangement. So first of all, we start with this number 1, 1. So 1, 1 starts from the atom of the sigma bond that is going to be broken, the one which is going to break down. Broken down and continues up to the atom, up to which atom? End of the pi bond system. Where pi bond, but must be in the conjugated. This numbering should continue up to that conjugated system. If there is some other pi bond somewhere which is not conjugated to the system, will not be here. Where the new sigma bond is going to be formed. So this end of the pi bond system where this new sigma bond is going to be formed. And so this number will be ij. It may be 1, 3, it may be 1, 5, it may be 3, 3, that we have seen. How do we number? So what happens here, if I go to the earlier, so this is going to be broken. So the numbering will start here. This one and this one will get 1, 1, 1. The one which is going to break down. And then continue, then 1, 2, 3. And this one also 1, 2, 3. It's going to this. So what happens here, as it is broken down, this shifting happens and we get this. The reaction happens here. So we call it 3-3 sigmatropic shift. That means the where the bond is formed, this is 3, this is 3. So that is going to be the number. So we call it 3-3 sigmatropic shift. In this case, which bond is breaking? This bond is breaking. So this is 1, this is 1. After this one, here we don't have any, so we don't go anywhere. There is no 1, 2, 3. As after 1, it stops because there is nothing more. But here we have to continue up to that pi system. So 1, 2, 3, 4, 5. So the shift becomes 1,5 sigmatropic shift. And this hydrogen. And here you see, this is a what is called cyclic transition state is involved. So transition state is involved. So here you have this cyclic transition state, which is involved here. And in the process, this is migrating. Now here, one thing you see here, that means this, suppose I have here deuterium. Now this deuterium is migrating from this atom to this atom. When it is migrating, at the transition state, what will happen? This will be in touch with both the atom at the same time. So our theory will tell us why it should. So because without touch of these two at the same time, this migration cannot happen. But when it is touching and one bond is breaking, other bond is formed. Bond breaking, what is bond? Bonds are formed from that overlap of orbitals. So here the orbital symmetry has to be conserved. That means you understand now this. That means this orbital symmetry, the orbital phase of this atom here and this atom here and this atom here must be same phase. Otherwise, if they are not same, that overlapping will not take place. So this is one thing that will come back when we take theory. Let us count these numbers, how we are getting. So this one, these two, I have already explained it, how we get it. So the same example I have taken. Now let us we go to some new examples. Are you getting my voice and is it clear?
Yes, sir.
Yes,
Okay.
sir.
So now here there are some reactions which go by name reaction also. This is called Cope rearrangement. This is Cope rearrangement. This 3-3 sigmatropic rearrangement sigmatropic shift of 1,5 diene. 1,5 diene. This is 1,5 diene. If I take this diene 1, 2, 3, 4, 5. This is 1,5 diene. This particular 1,5 in 1,5 diene, the 3-3 sigmatropic shift is known as Cope rearrangement. So this is what already we have seen one example here, and this also you see here. It takes place thermal. Why it takes place thermal? Then also, and we have already seen our pericyclic these polycyclic reactions. All the pericyclic reaction. In some cases, the reaction takes place under thermal condition. In some places, reaction takes place under photochemical condition, but here it takes place thermal condition. So we have to also understand why it is taking under thermal condition. So this is also important. So let us come to next one. Oxygen analog of Cope rearrangement is Claisen rearrangement. So this also you have done it probably in college also you have done this rearrangement, Claisen rearrangement. We have got, you see, by Claisen we have got another reaction called Claisen condensation. This is Claisen rearrangement. I think you have done it in your college also, but without understanding the real theory behind that one. That is also something like 1,5 diene, but there is an oxygen in between. So instead of one carbon atom here, there will be an oxygen. So that time we call it Claisen rearrangement. The typical example of this one is this. This is allyl phenol ether. This is phenol. This is allyl group. CH2, CH2, CH. This is allyl. So allyl phenol ether. Now you see here. Now What is your, this is Claisen rearrangement. And this here, what you have to understand most is that how do we get this number? 3-3 sigmatropic shift. This is a 3-3 sigmatropic shift. Here also, this is a 3-3 sigmatropic shift. Now, again, we have to identify which band is going to break. Without, and I mean, I'll be just giving some example also here. This one, so how do we, so you see the pi system here. This is a pi bond. The pi bond is not going to break. And identify that after pi bond, there will be a carbon atom which will be a residue. So whenever they, suppose there are two pi bonds here. After that, sorry, two pi bond. After that, there is, so that means this will be the bond which is going to break in the sigmatropic shift. That way you have to identify. You have to continue, just continue from the end of the pi bond system and then identify which is going to be the next sigma bond in conjugation. Not that if there is another sigma bond here, no. This is not going to be the sigma bond. Here, this is going to be the sigma bond which is going to break. So that one you have to identify. So here, you see here, one, so this becomes 1, 1. After you get 1, 1, identify that 1, 1. Then you go to the, count the number. So 1, 2, 3. Here also you count the number 1, 2, 3. So the number 3, 3 gets the bond which is going to be formed, the new bond that is going to be formed. The new bond that is going to be formed is a 3, 3 bond. Where is that? This is the new bond that is formed here. But in the process, we got this one, this particular intermediate, which will quickly rearrange because this is going to give us an aromatic system. So this is an extra step here. But this is, up to this is your, and so what it becomes? It becomes a 3-3 sigmatropic shift. And this reaction is known as Claisen rearrangement. So we have to come to details of Claisen rearrangement. Will come later. It is just introduction. Let us now, in the Claisen rearrangement, you have seen this. Here, if I just rub everything, here, if I see here, this has migrated to this allyl group has migrated to ortho position, where there was one hydrogen. But if ortho position is occupied, or both the ortho position with methyl group, it is occupied, then what we get? Where it will go? Any idea? Or will the reaction take place or not? Huh? Okay, this remains your task. You will identify this one and what is the product, how do you get it, what is the steps. So that becomes your homework. No doubt. Okay. Then we come to some examples. Let us take some examples. The first one I'm giving directly. So here again, you see here, we can very easily identify this one. This is the pi system. So this is the sigma bond, and from both sides, this is the sigma bond that is going to be put. So this gets 1, 1. So 1, 2, 3, 1, 2, 3. The new bond is going to form between 3 and 3. So we call it 3, 3 sigmatropic shift. And this is going to take place under thermal condition. Now, why thermal? We have not yet come to that. Once we take theory, we get this one. And this is going to be the product. So it will be a ketone, and the double bond will be there. And if we have this one, this is also a 3-3 sigmatropic shift. If it is 3-3 sigmatropic shift of this one, this also will take place under thermal condition. And this is the product that we get. You can have it here. This bond breaks here, this comes here, this comes here, and we get this product. So there is, this bond is broken down here at this point. We don't have a bond here. So this is 3,3 sigma. So this becomes, it involves the hydrocarbon also. So this becomes example of, another example of Pope rearrangement. And this one becomes a Claisen rearrangement. This is a Claisen example of Claisen rearrangement. All right, now you come. Now you identify. You give me the, this is the task. Just now you have to solve it. Just now you have to solve it. Give me, what is the migration? Sorry, what is the type of rearrangement? What is the shift that is there? And what is the product? Come on, quick. I give you 1 minute. Just 1 minute. Start. Just tell me the rearranged, what type of rearrangement? It is three. We got here example of 3-3 rearrangement. Then in one case we got 1-3 rearrangement. So what is this one? Quick. No time. We cannot spend time. You have to identify which is the sigma bond that is going to be broken down. And then you count from two sides.
3, sir.
3. No.
3.
Both are 3-3. Because two number has to be there. One is I and J. Is it 3-3 or something else?
Sir, 2-3, sir.
Is it 2-3? Any other answer? Any other answer? Now you see, just see. Okay, let me just start. Somebody telling 3-3, somebody one answer I got 2-3, and that's all. Any other? 3-2. 3-2, 2-3 will be same. Whether you write it this way or that way, that is. Okay. Now, see which is the sigma bond. You start from the pi bond. This is pi ending here. Then this is a sigma bond. After that, this one. So this, and from here also the pi system starts here and then goes here, then goes here, then this sigma. So this is the sigma bond which is between the two pi system. So this becomes your 1-1. So go this way. This is 2. This is 3. And come this way. So 1, 2, 3, still there. 4, 5. So it is 5-3 sigmatropic, 3-5 sigmatropic shift. Not 3-3 or 2-3. See this. 3-5 sigmatropic shift. Not 5-3, 3-5 sigmatropic shift. Hello. So this is what is the challenge. And this also will take place under thermal condition. We have to identify why it is thermal condition. This is how it happens. This is the product. All right? Hello?
Yes, sir.
Yes, sir.
Yes, sir. So now you have to be careful. Okay, some more example are coming. Now here, now this also, you tell me. This is also an compound. You tell me what is the rearrangement, the number first, and then the product.
5-5.
This is
5-5.
5-5. How many of you are telling 5-5? I'm just getting the people, those who are answering, they are the one who are answering always, not the other one. Other voice I'm not hearing. Yes, it is 5-5. Just see where which you have to identify which sigma bond is going to break and where the new sigma bond is going to form. So how to identify the sigma bond that is going to break? Just start from the pi. This is pi, then sigma, then again pi, then again sigma. After that, the sigma bond that is there. and that must be in conjugation with another pi system. So this is the bond that is going to break down. So this will get number 1. So 1, 1. And count this way. So this is 2, this is 3, this is, sorry. This is 4, this is 5. This way, when you count 2, 1, 2, 3, 4, 5. So this becomes psi 5 sigmatropic shift. And what will be the product? Product very easily you can identify. This is the new sigma bond that is going to be formed here. Then it comes here, then it comes here. So what we get? We get this one. This double bond will be here, then double bond, and again another double bond. Then this one, a double bond here. Then again, double bond here. And there will be an OH. Is it the product? Is it the product?
Yes, sir.
No, I say no. Why not? Tell me.
So which group migrated?
This is enol. Enol cannot be there. So it will tautomerize to keto. So you get the keto here. So these things, basic chemistry, you don't forget. So you get the product here. So this is a 5-5 sigmatropic shape. See here, this is a 5-5 sigmatropic shape. And this is the migration that we get. The new bond is formed here. It is a 5-5 position. So it is 5-5 sigmatropic shape. But here, because the enol has formed here, so this will quickly rearrange to keto. So this is the final product. So this type of fundamental chemistry you should not forget. So this is the, I think you got it. All right. So I move forward. What is next? Okay. Now let us come to theory. Let us come to theory. Now, in the theory, what has happened? Okay. In theory, what happens? We take an example of 1,3 sigmatropic shift of hydrogen in allied system. With this one, we understand the theory. Okay, this is the example. So what is going to happen here? This is the allied system. This hydrogen is going to break down the hydrogen bond and the hydrogen will migrate here. You may say that we are getting the same product. Yes, we are getting the same product, but if we change it to something else, suppose deuterium, and this carbon is, suppose it is radioactive carbon, if it is there, then this CH bond is going to be, can be identified as a different atom, a different bond from this one. Anyway, so this is, I think you understand this one. This is the allied system which is there. Now, what happens in the process? How do we identify that? What it is migrating? It is the hydrogen which is migrating. So hydrogen, we can consider it to be that this is the sigma bond which is breaking down. All right, this is the sigma bond which is breaking down. So this sigma bond that is there, we can consider that it is breaking down into 2 halves. So that means it will become an what is called radical. So one part will be allyl radical, and other part will be hydrogen radical. So this is the how it breaks down, allyl radical. Now this allyl radical will be having its resonance with because this electron will keep on distributing itself along these 3 atoms and this hydrogen. So what will happen in the orbital symmetry when we consider this will be overlapping between these 2 terminal carbon atom 1 and 3. At one point, this hydrogen will go and bond with this one, and we say that there is a migration of this hydrogen atom. And so it is 1,3 sigmatropic shift of hydrogen in allied system, in 1,3 allied system. This 1,5 also, 1,5 allied system also can be here. The same thing. So what we see here, what we see here, this is 1 hydrogen bond. Just consider that this is breaking down, so it is coming out with its electron. This 1 electron will be there. So this one is hydrogen electron. This 1,5 allyl system will be again that is there as a radical and hydrogen. So then this hydrogen will be migrating from position 1 to 5, but during that migration it has to follow all the rules of pericyclic reaction, orbital symmetry, etc. This is so we are going to study. Then we have to see whether the reaction is going to take place under thermal condition or under photochemical conditions. So this also we have to understand. Okay, so let us see now next part, that is molecular orbital of the system. So first of all, we have to go to the molecular orbital. So when we talk of the allyl system, there will be, we'll have how many? Allyl is, what is allyl? Double bond. And this is 1 electron here. So how many electrons are there? 5 electrons. How many will be there? How many orbitals will be there? Sorry. How many orbitals? This pi bond will have two p orbital, 1 p orbital here, so the pi bond. And this radical also will have 1 p electron. So there will be 3 what is called p orbitals, pi orbitals. P orbitals. So we'll get, once we have 3 atomic orbitals, we'll get 3 molecular orbitals from 3 orbital having the energy distribution of electrons as below. Okay, let us see. This is what we have also done with allyl anion, but here it is allyl radical we are doing. So if it is allyl radical, so these two will be coming from the pi bond, and this is from the radical that is there. This 1 electron is there, very tiny, which is not very much visible here. Okay, so this is the electron. So 3 orbitals. So molecular orbital, how many we'll get? We'll get 3. So psi 1, psi 2, psi 3. But total how many electrons we have got? We have got 3 electrons. So 3 electrons, first one will get 2 electrons, then second one will have 1 electron. So this psi 2 becomes your HOMO in ground state. That means without excitation. But if you do excitation, means if you give photochemical energy to this one, this electron will jump to this, right? So that time the psi 3 becomes HOMO. And this is just like allyl anion. In allyl anion, we had 1 pair of electrons here, so 2 electrons, but here it is not having, it is having 1. So this is very similar to your allyl anion. And this also will be having this. This is a p orbital, but is perpendicular to these 2 orbitals. So there is no overlapping here. So we call it also this is something like non-bonding orbital. This is bonding orbital. And this is your anti-bonding orbital. But these terms are not useful for us. Will be useful term is your HOMO and LUMO. So that is important. Okay, so now you remember this one whenever we, and so what we see, psi is the terminal lobes are antisymmetric, but when it becomes photochemical condition, the terminal lobes are going to be symmetric. Now what happens here when the hydrogen migrates? So hydrogen is going to come here. Okay, now I'm not exactly this one. We have to identify which one is your HOMO. So hydrogen is having what is hydrogen? Hydrogen its electron is where 1s, right? 1s electron, so 1s1. So it will have a spherical orbital, and it will have this phase. So suppose it is, we can identify it as positive phase, and say here this is, if I consider positive, this is negative. So this one also, if I give shade, this is same phase as this one. So if I give it as positive phase, I have to write here also positive. But once we write positive, negative, it looks like that it is a charge, but they are not charged, they are phases. All right. So if the bonding situation has to happen, this two hydrogen which this hydrogen which is there has come out as radical must be in a position to overlap with the orbital with the same phase. If they are of opposite phase, because it has to overlap at the same time, because this migration. So if these two terminal lobes are not of the same phase, this migration is not going to happen. So let us see the situation. Here, in the transition state, hydrogen atom must be in contact with both ends of the chain at the same time. I think you got that point. This one I'll be forwarding, not now, after we cover a little bit, and then I'll forward it. So what is the situation? So suppose the terminal. Now you see, we are not, I'm not telling that this is homo or lobe. If our terminal lobes are of this nature, this phase and this phase are same, that means it is symmetric. The hydrogen comes with its electron, is also having this phase. Then when the overlap happens here, both sides, okay, both side overlapping happens here, that time we call it suprafacial overlap, suprafacial. But suppose it is not here, this is inverted. Suppose it is inverted. So if it is inverted, so that becomes anti-symmetric. That time the phase of this phase of hydrogen will have overlap with this phase here, down there. So that time the what is called is going to be interfacial addition, interfacial migration. Okay, this is what we are going to get it. Just see next. First of all, now 1,3 migration we have not yet. In our example, did we get any example of 1,3 migration? No, right? We have taken 3,3, then we have taken 1,5, then we have taken 5,3 migrations, right? 5,3 shift. There was no example of 1,3 sigmatropic shift. But here, for the sake of understanding the theory, we have taken this 1,3 sigmatropic shift. So if this 1,3 sigmatropic shift is going to happen, but under thermal condition, what we find, this has to be like this. This hydrogen will migrate here, the hydrogen will go here, and we get this under thermal condition. And what is found? It does not happen. So it is forbidden. But only telling is not sufficient, therefore we have to understand it. So we come to next part, that is, you see here. You know now what was homo? Homo was Shy2, yes or no? Of this align? Yes or no?
Yes, sir. Yes.
And Shy2. And Shy2 was what? Antisymmetric. Antisymmetric. And the hydrogen is coming with its lobe here with one phase, say in our picture, say blue phase. So it will have overlap with this one, but for migration, this also should be at the same overlapping, same phase. So it is not going to happen. So this migration is going to be forbidden migration. So what is our under thermal condition? So thermal condition, or this is Shy2. So therefore, the conclusion is that therefore thermal, thermal 1,3 suprafacial. You see, coming from the same side, it is not getting. We are not thinking in terms of getting this way. Suprafacial. The suprafacial sigmatropic shift is forbidden. Thermal 1,3 suprafacial sigmatropic shift is forbidden. Are you satisfied with my wordings here? Hello?
Yes, sir.
Okay.
Yes,
But
sir.
yes, sir, and no, sir. I am just getting for just few voices, not from all. Okay,
Sir,
let us see now here.
sir,
Yes, Bolo. Yeah.
sir, can you explain once again, sir, first one?
The first one you see here.
L.
Now, you see what to form this migration, because this hydrogen is going to migrate to this. This hydrogen which is going to migrate from this carbon to this carbon. In thermal condition, which one is involved is your HOMO is involved. So HOMO of this one, and hydrogen also will come with its orbital with its electron, that is also HOMO with this one phase here. That is, we are identifying it by this marker, or we can identify it by positive. But for positive, if I give positive here, that means I have to tell this is positive and this is negative, and that case this becomes negative and this becomes positive. But we are not using both these terms. We are using. So if the migration has to happen, if this hydrogen has to migrate from this carbon to this carbon, because this is what is migration, sigmatropic shift. It is migrating. So this has to jump from here to here, having the same phase. So this phase here is matching with this one. So this is all right, but this is not. The HOMO of this one is not having the same phase. So this migration is not possible. So, and this is
Yes, sir.
same, I mean, without any alteration. So we are coming. So it is suprafacial. But how this phase will become same if this hydrogen overlaps with this lobe of the carbon, having the same Psi2, HOMO remaining same. So thermal condition, it is Psi2. It is antisymmetric. We have already identified that one in the last slide. Now here, this one, if it has to migrate, if it has to maintain that orbital symmetry, it is possible here. This is blue, this is blue, our blue is here. So that becomes what? This becomes interfacial migration, interfacial. So what is allowed is interfacial sigmatic shift is symmetry allowed, because for bonding to happen, they must have the same symmetry, same phase overlap, same phase overlap. So symmetry remains same. All right. So it is interfacial is allowed. But in the process, what is going to happen? You see here. So how this atom, so what will be your transition state? Transition state will involve one atom here, two atom here, three atom here, and that, so 1, 2, 3. So this is, but this is not going to be geometrically possible. So geometrically, it is, the space is too constrained here. This transition state is not going to be possible. So that becomes geometrically forbidden. Thermally, I mean, symmetry allowed, but geometrically forbidden. I think you got my point.
Sir,
Yes.
sir.
Yes.
So it is geometrically forbidden
Yeah.
under thermal condition. So
Condition.
transfer migration of hydrogen in the first reaction is possible or not?
No, first reaction, what we are only using the same reaction. Here also, because this is one case, this is a second case. We are just different cases we are discussing. Suprafacial, that means coming from the same side. Interfacial means opposite, is going below. You see here, it's going below. It is on the top. So that
In the
becomes,
previous,
no.
we know that interfacial symmetry allowed is when interfacial symmetry allowed takes place, then reaction is not take place.
Yeah, it is not, reaction is not going to take place. That is why geometrically not possible. Geometrically
Therefore,
forbidden.
sir, reaction under thermal condition, migration of hydrogen is not possible.
Yes, that is what our final conclusion is, that one.
Okay, sir.
So this is, you see, this is suprafacial, it is forbidden. Interfacial is allowed, but geometrically not allowed. Symmetry allowed, but geometrically not allowed. That means ultimately it is not going to take place. That is the simple conclusion. So our conclusion is that thermal 1-3 migration is not possible. Okay.
Yes, sir.
If thermal is not possible, then what is possible then? Okay. So here, this is,
Middle.
now you see, this is an example. This is a triene having this cyclic. Now, out of these two molecules, which is more stable molecule? Tell me. This is the, if we expect a product. So this one and this one. If this migration happens, if the migration happens, which is possible, what is the, we get this product. So which one is more stable? The product is more stable, or the structurally or thermodynamically, which is more stable? The product is more stable, or the reactant is more stable? Tell me.
So reactant maybe. Allylic system is more stable.
Arey baap, how can you say that one? Your chemistry is going to be then very dangerous. This is aromatic system. Is it
Product
aromatic?
is stable.
Product is more stable. This
Yes, sir.
thermodynamic,
Aromatic system.
this is aromatic system. So you should
Yes.
quickly identify that those type of parameters. No, this is non-aromatic system. If it is there, it is a triene conjugated, all right, but that conjugation here, it is much more effective resonance here. So this is aromatic. So this is much more stable than this one. But if we have a system like this is not going to, and we just heat it, it does not go there. It is not going to, though product is more stable than this one, but we don't get the product. Why? Same reason. If it has to go, this migration has to take place from this side. That means from the top, it has to migrate to the bottom. So there will be a transition state of involving how many atoms? 1, 2, 3, and 4. 4 atoms. 4 atom transition state will be there. And that will be a very, very highly strained transition state. So geometrically not possible. So this does not happen. This is simply as that. This is an example. So 1-3 sigmatropic shift is thermally not allowed. If thermally not allowed, then photochemically let us check. Then 1-3 sigmatropic shift under photochemical condition. Let us see photochemical condition. Let us see what happens. I'm not getting any warning today. Why? I don't know. This one, you see, in photochemical condition, the allied, what is homo? Now homo becomes Chi3. Yes or no? In Chi3, these two are same phase, symmetric, and the hydrogen radical having the same, it's what is called orbital, atomic orbital is the same with the same phase. So what, for the migration, what has to happen? It must have same time, it must be bonded to both. And if this orbitals are of the same phase, then this is possible. So what happens? So what is our conclusion? Therefore, photochemical 1-3 suprafacial, you see here, is coming from the same side. It is not inverting. Sigmatropic shift is allowed. If it is allowed, let us have an example here. This is an example where we have it. You see, this one quickly take place. This is suppose the reactant. Now here we have here, this is 1, 2, 3, and bond, you see here, this is 1, 1. I should have given 1 here. So this is going to break down, and where it is going to migrate, is going to migrate to this atom where we have this, it will take up this one. So we get this product, but under photochemical condition. This happens only. If you give thermal, no, it does not happen. It does not go. So it will take place under photochemical condition. I think you got this. All right. Hello.
Yes, sir.
Yes, sir.
Okay.
Yes, sir.
After that, we have to go to 1.5. So 1.3 we have checked. That 1.3 is, what is the conclusion? 1.3 is sigmatropic shift is thermally forbidden, photochemically allowed. But in thermal condition also, what is allowed is superficial is forbidden. Interfacial is allowed, but interfacial though allowed, but is geometrically forbidden. So these are the parameters that you have to understand. So this is 1.3. Then we have to go to 1.5. Today we are just on time. It is 1.5. Then we have to, and once you understand 1.5, then you will understand all. Then what the examples that we have got: 3.3 sigmatropic shift, then 5.5 sigmatropic shift. So then we'll come to a general rule for this sigmatropic shift. So that's all. So we'll be having more examples and then other different types of reactions which are there. And then I'll give you some problems. Some problems are set on in the NAT examination also. So I'll forward it to you. So you have to have a practice on that one. And then we'll just, so today's, I don't know, this, our time has just, so we end this show, discard this, all this. And so I come back to the video mode, stop sharing. Why I find now 26 means 25 people are there. The rest, what happened? The rest of the people, they have migrated, I mean, they have left or they have. So what is your, have you understood this? I'll forward this one up to today's lecture. I'll forward this and then we'll the second part I'll include. Otherwise you may forget your first part. Or I may include some more. Say 1.5 I'll include, because once you have understood this one, 1.5 you can also understand. Yeah, then we can also. So let me see how I can forward it. But from Monday you start your practical class, and after that we'll also meet in the campus. Monday I'll be also going. Yesterday I went there. We had a meeting with VC. So there are things which are going to be somewhat different now. So, okay. So I end this meeting here. You join your next class after. All right. So all the best.
Yes, sir.
Okay.
Thank you, sir.
Kannaki, you just forward me the attendance, including those who were there earlier also.
Okay, sir.
Anything you want to say? Anybody? Okay. We'll be meeting in the campus. So I expect that all of you are there. Okay. You can ask me their question also.
Okay, sir.
Okay then. All the best. Good.